All right, so recently I made a post on my Instagram page that said, base 10 mathematicians aren't playing with a full deck. A hand of cards, and it stops at the jack, and there's no queen and king. So the implications are there are things missing within the realm of base 10 mathematics that only exist within the scope of base 12 mathematics. So what do I mean, and what am I talking about? Well, what I'm talking about is a dodecagon, the geometry of what I'm going to call the base 12 dodecagon. So this is a dodecagon that you can basically draw on graph paper. It's really easy. All of the points that define its shape are actual lattice points, and all of the sections of dodecagon are the same length, and they are the length of 0.5 root 2. So anybody can draw this pattern. As I say, you can draw it on a graph paper. It's very easy to draw, but the implications of its importance, when we start to question the base at which we approach this with this diagram, in base 10, you can take your graph paper, you can create a base 10 grid around this shape, and you can see what the relationship is between this dodecagon with sides the length of 0.5 root 2 in base 10. And then you can alter your lines a little bit and see what the difference is if we approach the same geometry from the base 12, from a base 12 perspective. So what it seems here is when we do this, that we make our 1 larger, because now it has 12 units instead of 10. And we see that the relationship between the dodecagon and the lines that represent the 1 changes. So it's important to realize that when we convert from base 10 to base 12, the actual length of 1 isn't changing. It appears to change when we're working on graph paper, but that's because the small squares that we're working with aren't changing. So in these two examples, the 1 is actually the size of our little squares on the graph paper. But in reality, the length of 1, or the size of 1, doesn't change. It's the length of our decimal places that's changing. So if we think about dividing the 1 into twelfths instead of tenths, then we realize, oh yeah, of course, 0.1 in base 12 is going to be a shorter unit than it is in base 10. So what happens in reality is this dodecagon pattern shrinks down as the length of 0.5 root 2 becomes shorter in base 12 than it is in base 10. So when that shape shrinks down, it actually lands on the 1 in a way that it doesn't in base 10. So suddenly this pattern, which seems like to sort of exist floating on the Cartesian plane, in base 12 it becomes anchored on it in such a way that no matter what number you think of, any decimal place on the x-axis is going to have a corresponding dodecagon attached to it. So in base 12, this dodecagon pattern completely permeates the Cartesian plane. It's anchored throughout the Cartesian plane in a way that it just simply isn't in base 10. Similar to how the triangle with the sides of 1 and 1 on either side of the right angle, then the square root of 2. That's a foundational triangle that exists throughout the Cartesian plane. Anywhere where you go along the x-axis, you can go up the y-axis, you'll find the same length, you'll find a point, and the distance between 0 and that point is always going to be in units of square root of 2. Same with the special right triangle with the dimensions of 1 and 2, and then the square root of 3. These are foundational geometric elements, and so too is this dodecagon in base 12, and it doesn't have the same power or presence in base 10. And from this dodecagon, we can create a diagram that generates all 360 degrees around the circumference of a circle. We can basically plot points on the circle, as many as we want, using this geometry, and we can't do that in base 10. So this is a foundational geometric pattern that only exists in base 12, and unless someone actually takes the time to explore this geometry, it's a tool that we are unaware of. It's a foundational element that nobody's aware of, and unless you embark on a journey of exploration within base 12, you're never going to find it. And so the question comes up, does the universe have a base? And the answer is yes. The universe has a base, and it's base 12. And we kind of know the circle has a 12ness to it. When we use simple geometry to start playing around with the circle, this pattern comes up, and this pattern naturally divides the circle into sections of 12. So you can see here, if we travel along the circumference of the circle, we have access to pi in its decimal form as 0.1, 0.2, 0.3 in base 12. Again, in base 10, it doesn't work out that same way. Base 12, it's smaller size decimal places. So that's all I'm going to say for this video. I just wanted to introduce you to the idea of the base 12 dodecagon. It's a rich geometric pattern that has it has the potential of answering a lot of questions and solving the problems that would come up with infinity. It ultimately becomes the geometry of the smallest particle. That's where this is going. That's why not only are mathematicians not playing with a full deck, base 10 physicists are also not playing with the full deck. They're missing this key geometry because it's in base 12. So in a sense, physicists have been let down by mathematicians because everybody's in base 10, and base 12 is the math of the universe. Okay, so I'm going to leave you with that. Thanks for watching.